We're delighted to have Guilherme Pimentel visit us from Escola Normal and tell us about kinematic flow and the emergence of time.
Okay, thank you. So maybe let me make a poll because there are lots of young people here. The old people I know this stuff, but who knows about inflation, inflationary cosmology? Raise your hand. Okay, so I need to do the proverbial quick introduction. Let me just spend a few minutes with this. So before I motivate, maybe I should tell you the end. So what is the goal of this talk? The goal of this talk is to strip down the intricacies of cosmological perturbation theory to a toy model where we can say quite a bit about the structure of cosmological correlation functions. And then we discover kind of a cool pattern that you can kind of bootstrap your way to find the statistics of these primordial perturbations without ever referring to time evolution. So emergence of time maybe is a bit too much of a slogan, but the bottom line is that there are some intrinsic rules to find differential equations that only depend on the spatial distribution of the inhomogeneity. So I'll try to explain how that works. It's based on two papers. Actually, I just realized that the first time I ever talked about this was here. It was 2021. It was during the pandemic. It was QC limits gravity. It's interesting that. And now it'll be the first time I talk about this paper that is going to appear very soon, where we realized that we made it too mysterious in the first paper. There's a new basis in which the story is super simple. The rules are provable, and you can even learn by yourself. And then you can go home and draw some pictures and find differential equations and so on. It's kind of neat. So I hope to tell you about this. But I need to strip down. It's like I want to talk about the beautiful Christmas tree, but in the end, I'll talk about the skeleton. Okay, so let me talk about the motivation, and then I'll step backwards to a tractable model. So the motivation are the initial conditions of the universe. So no big deal, just figuring out the birth of the universe. So that would be nice to understand. And to understand that, we look at statistical properties of stuff in the sky. So here we are, us, and we observe stuff around us. So like galaxies. These are my little galaxies at large scales. And in fact, I was just telling people at lunch that today, probably today, like 100 kilometers away from here, there will be this experiment called SphereX that is a galaxy survey that's going to try to measure deviation from Gaussian statistics of the initial conditions of the universe.
Do you mean literally today?
Literally.
It started today.
Well, no. It was supposed to fly a couple of days ago, and it was delayed. And today there's a window to be launched for it to be launched. Forget the name. Vanderburg. It's like the base that is 100 kilometers away from here. So maybe we'll see some tracks in the sky. It will be SphereX. So this is a galaxy survey that measures galaxy clustering at very large scales, and it's very sensitive to nonlinearities of the initial density field. And here, okay, so what's the kind of observable that you're interested in is, say, the two-point function of the density. So you do number counts. It's a proxy of the amount of dark matter. So we know that the galaxies are under some scaffolding, some cosmic web of dark matter. So the galaxies are a proxy how much dark matter there is around a certain region. And then you study the two-point function as a function of wave number, and you get some beautiful curve that goes up, goes down, wiggles, and you take a whole cosmology course to understand the properties of this curve. And likewise, if you go, there's a whole dark age of the universe that we don't really observe directly, that we hope one day human beings will have the ability to observe. That would be more or less 1 million CMBs worth of data, but not today. And then if you go backwards in time, you have the CMB, for which you've probably all seen this Planck map of the temperature perturbations. This is all normalized by the average, no average density and average temperature in the universe. And you see these acoustic peaks, very beautiful, of the hot plasma. The temperature perturbations are order delta T over T bar, the actual order 10 to the minus 5. And to explain the data, you need very simple initial conditions at time equals 0, what we now call the hot Big Bang, because we don't think it's the beginning, even though for the standard cosmological model, you just start the clock here with some initial density field or the Newtonian potential, the curvature fluctuation that's almost scale invariant, the functional wave number, it's almost flat. It has some amplitude, AS, and it has a very small slope, some scale dependence, that for bizarre historical reasons we call number close to 1 minus 1. So this is of order 10 to the minus 2. This is measured more than 5 sigma by Planck, and AS is order 10 to the minus 10. So because the 2-point function, it matches with this expectation of the typical size of the temperature perturbation. So this is all we know, but it's Gaussian statistics, so it's just a 2-point function. And it's imprinted here at the hot Big Bang, which is a causality puzzle. How come you have correlations over long distances at time equals 0? So we fill in the timeline with this earlier phase that the universe undergoes accelerated expansion. So this is what we call inflation. And then we explain the picture through just the Schwinger pair production. Okay, it's just there's some scalar field that drives this expansion, and then it's pair produced, and the kinematics of the de Sitter space or quasi de Sitter space, whatever this inflationary phase is such that it's almost wired in this almost scaling variance here. So all we know from this is all we know from the data today. Everything else we have bounds on. So for example, the fact that it's a gravitational theory implies that there are also primordial gravitational waves. Now this figure is getting busy. Is there an eraser? Thank you. Yeah, these are hard to find, but I had to buy one in the US. They don't have them in Italy. Oh, I like them. So let me stretch the figure. So for the rest of the talk, so this is beautiful, very nice. Lots of beautiful physics comes in here. But for the rest of the talk, I'll just focus on this part. So, I was trying to show that the universe is undergoing accelerated expansion, but I'll just focus on this slice, and I just described it to explain the data. All you really need is a very light, almost massless scalar field, free field on top of this geometry. But for example, we know that there should be gravitational waves. We don't know their strength. We know that their 2-point function is at least less than percent level, 5% of the 2-point function of the scalars. We're trying to measure them now. We'll try to measure them as satellites in the next decade. And sphere X, that is about to fly today, is going to hunt for 3-point function, very special type of 3-point function. Now, at 3 points, you could imagine doing all sorts of things. And so, for example, so what are the possibilities? So maybe the two extreme of what could happen is you just probe some self-interaction of these scalar perturbations. So you learn something about the effective Lagrangian of this theory, or you discover a new state. So, and sphere X is hunting for the most extreme type of exchange diagram, one that is mediated by a massless particle, because it allows you to couple these perturbations at arbitrarily long distances, paying as minimum a price in redshift as you can imagine. Okay, so this is a mass much smaller than the Hubble scale during inflation. So the lighter the mediator, the longer you can couple long perturbations and short perturbations. So let me explain why in this diagram time and space are traded with each other. So the idea is because the universe is expanding, stuff that is pair created earlier on is stretched more. So if I look at a diagram like this, these guys got stretched just a tiny bit because they were pair produced towards the end of inflation. Well, this guy was pair created earlier, so they are stretched over very long distances. So if I can correlate long modes, long wavelength modes with short wavelength modes, is because there's a messenger. And if the messenger is heavy, its power is redshifted away. This is a very small process. And as it becomes lighter and lighter, this coupling becomes more efficient. Okay, so these limits of hierarchy between modes probes the light spectrum of whatever is active during inflation. Well, so why the heck would you want to, why would you be interested in this? Well, that's all we really know from observation. So we know that there is a curvature perturbation. And it's some sort of Goldstone boson from time translation symmetry that's broken by this background evolution, okay? And we don't know, and there is a nonlinear sigma model that describes this this Goldstone boson. It's in the literature, it's called the EFT of inflation. And the question is, what UV completes it? And well, we know in particle physics, there are two broad ways of UV completing a nonlinear sigma model. So way number one is through a linear sigma model. And so that's how it works for the Higgs, how it works for the electroweak sector of the Standard model. And so this is the way that 99% of the literature in inflation is focused on. So it's called slow roll inflation, for example. So it's the simplest example of this type of UV completion. So if you ever saw any talk on inflation, what people typically do is they draw some scalar field rolling down a hill. There's a little potential here. Then there's a scalar field, and then the scalar field rolls down the hill, and that's great, but we have very little evidence that this is our universe, okay? We know about this guy. And this is a way of UV completing the theory of this guy. So the scalar field does double duty. Its potential energy drives the expansion of the universe. And then its tiny quantum fluctuations are converted into this curvature perturbation, okay? Very interesting, very nice. It's very simple, calculable, and so on. But you could imagine that this has extra degrees of freedom, just like, you know, we have the Higgs plus other particles. It's extra degrees of freedom. Then what's their purpose in life? Or you could even imagine that there's another way, some QCD like strongly coupled way. And here, almost nothing has been done, and we don't even have a benchmark model of what that would look like. I just want to make this analogy to point out that it would be interesting because presumably then, if this is a type of UV completion of inflation, it should leave some interesting observational imprint. And just as a little advertisement, if you have a model that UV completes inflation in a different way, you can constrain it right now, not tomorrow, not in a decade, with existing data. Because the way we put constraints on these types of UV completions is not very different from gravitational waves. You need to know what you're looking for. So it's not that we measure the 3-point function, the 4-point function of the data, is that I need to give you from theory or from some motivation what the 3-point function should be like, and then you match with the data and see if it's consistent or inconsistent with the data. So there is a new proposal where we have many templates. They're motivated mostly from this angle. Slow roll inflation plus adding maybe sprinkling extra degrees of freedom. But maybe there is something else. Maybe there's a strongly coupled sector with an interesting 2-point function here. And then you could give you some new observational imprint. So anyway, so this is the main motivation. Okay. Questions? Yeah.
One like you can also describe the data. What do you need a master for?
No, you don't. You don't. It's just that. Well, so inflation happens at a certain energy scale that we don't know, right? So, for example, so why do we care about measuring gravitational waves? Maybe besides the fact that it's cool that you're measuring the growing pains of the universe, right? The universe is expanding and then shearing and so on. That's what these gravitational waves are. You have access to H inflation because the 2-point function is very robustly controlled by H inflation over M Planck. So we know that this is the typical size of this perturbation. The gamma is less than around 10 to the minus 6. But if it's around the corner, then it means that you're just 6 orders of magnitude away from the Planck scale during inflation. So that's a huge opportunity to do particle physics, right? We imagine that even if there's stuff that is neutral under the standard model, maybe couples to the inflaton-tree level or loop level, and stuff that is produced at 10 to the 13 GeV will be efficiently produced during inflation. So that's, yeah. Why there are 3 generations, I have no idea, but there are, right? So maybe there is stuff going on at very high energies, and you could imagine using inflation as a particle detector.
Is there a theoretical lower bound on how big the graviton has to be?
Theoretical lower, well, you.
Can they make it? Like
Yes, I mean, it can be insanely small. Okay, it can be 10 to the so the tensor to scalar ratio. To this ratio here. You can reheat, for example, at temperatures in order to drive Big Bang nucleosynthesis, and then R will be 10 to the minus 60. We know that R is less than 10 to the minus 2 right now, so the current bound is 10 to the minus 2. The reason why we plausibly think that we might be around the corner is driven by simple models. So if you write a model, this is a parenthesis, okay? No. Parenthesis. So if you write a simple model of slow roll inflation, then it turns out that an S minus 1, that is of order 10 to the minus 2, is controlled by 2 things that are related to the slope of the potential. Okay, it's like I don't remember, but it's something like 4 epsilon plus 6 eta, where you don't expect these 2 numbers to be very different from each other. And then in slow roll inflation, single field slow roll inflation, R is of order epsilon. So because this is measured 10 to the minus 2, and you don't expect a huge hierarchy between these guys, then you have a strong bias that you're close to detection. And of course, if it's true, it's spectacular, right? Because 10 to the minus 2 implies that H inflation is 10 to the 13 GeV or something like that. But from the point of view of just having inflation and explaining our universe and so on, you can model build to put this all the way down to the very, very low energies. Yeah. Other problems kick in if you do that, but end of parentheses. Okay, so this is the motivation, and a lot of my research activity has been about trying to understand this from the pheno side, but also from the theoretical side, just from the formal. It's an interesting object. It's some sort of generalization of a scattering amplitude, but in curved space. Okay. And somehow the working horse for this sort of precision computations of this type of cosmological correlators has been the idea of boundary differential equations. So let me explain that, and then I'll get to the main model of the talk. So the problem is how to compute cosmological correlators beyond 2 points. So if I have, for example, self-interactions, or I have a messenger, this. So, oops. This is now more or less a solved problem. So at 3 level, we understand how to do this computation. It was an open problem still, not that long ago. And here, in this direction, you could imagine now going beyond 3 level. So you could imagine branching out in different ways. So what is the frontier, if you wish? One thing that one could do is study the one loop, a bubble diagram like this. Can I compute this? And for the bubble, it's okay. The moment you put a triangle at one loop, it's already all hell breaks loose. It's an open problem. And or you could imagine going this strong coupling way. And what happens, for example, if I have some strongly coupled sector and I have an interesting operator and I put it here in the exchange diagram. So these are open. Okay, so this is understood. More or less understood. Of course, there are little things that are not fully fleshed out. So this is open. Somehow here it's understood, but it's understood that the best way to do it is not through explicit time evolution. So the standard way, standard formalism to compute this is actually called the Schwinger-Keldysh formula. It's not that I prepared to say Schwinger many times. It's just amusing. So it's called the Schwinger-Keldysh formalism. You just do time integration of these variables, unlike in scattering amplitudes where you can immediately diagonalize all the isometries, go to the center of mass frame and so on. In cosmology, even at 3 level, you need to do some integrals just to integrate the time evolution. And but somehow these time integrals are hard. And there is an analogy that I'll try to make precise for the toy model. That, you know, when you compute, for example, scattering amplitudes beyond 3 level, then you run into loop integrals, and then the scattering amplitudes people have taught us that a nice thing to look for are differential equations that the integrals satisfy. And here a similar thing happens, that instead of doing time integrals, eta 1, eta 2, integral over eta 1, eta 2 times some propagators and so on. So this is some function f. Instead of doing the explicit time integral, say from -infinity up to the point of observation, star, you trade that for some differential operator that annihilates f. And then you try to understand this. And this differential operator will depend on the kinematical data, which are the locations of these perturbations. Okay? And so this has been the best way to compute this in practice. And when we first realized this now 7 years ago, more or less, the immediate reaction was that these differential equations only exist because of symmetry, because the differential equations are related to sort of the Casimirs of the Sitter group or of the boundary conformal group. But then this differential equation phenomenon kept appearing, like you can For example, you can start breaking symmetries during inflation, you can break boost symmetry, you can change the dispersion relation of these particles, and they're still there, So the question that this work, this kinematic flow was trying to address is, are there differential equations in more general setups? And I don't claim that they always exist, but the answer is yes. There are. And I'll explain a toy model where you can do that. Okay, so that's where I'm going. So we're detaching slowly away from the real world, and I'm gonna tell you about some beautiful mathematical physics. But questions?
Sorry, just to get my head around.
Uh-huh.
So these calculations you have to do in the UV theory, like you have to pick some UV theory that UV completes your nonlinear sigma model, or like how much can you do in the UV?
No. I mean, for example, if you work in the Sitter space, then you don't need to, right? Because if you know, for example, the answer for a massive scalar, then you know it for any spinning particle. You can use the Sitter isometry to find essentially all possibilities here. And then your job as a model builder would be to choose which masses and which couplings and so on. This is more a theory of shapes. Then the UV completion would be about what's the field content and what are the coupling constants and so on. Well, here I'm more trying to understand what are the kinematically allowed correlation functions. They're consistent with the cosmological dynamics and unitarity and so on, independent of the UV completion. Because the observables that we care about are so crude. There's a 3 and a 4-point function and weak coupling. You could imagine trying to come up with the whole menu of possibilities. Okay, so that's the idea. Of course, then if you take a specific UV completion, then it would imply that these couplings are some specific number and they're only particles of certain mass that appear and so on. That's not my goal here.
You're not like
It's kind of like-
saying like how many derivatives of particular coupling of this blue line to this wiggly line.
No.
Whether it's like a photon or a graviton or whatever. It's just
Yeah, for example,
some particle.
in pure de Sitter space, it's irrelevant, right? Because the 3-point coupling is unique. And once you know it for scalars, you can find it for any spin. Then if you break boost, then you can essentially take one of these diagrams and keep sprinkling it with derivatives to generate all types of cubic couplings and so on. So you can do that if you want. So the goal is just to find, I have, for example, here are 4 points, 1, next 3, next 4. And the question is, what are all the f's of x1, x4 that are compatible with, so this is the question, what kind of functions can I draw that are compatible with this type of diagram, okay? It's not that I can write any function. There's a subset of functions that come from unitary bulk dynamics. So that's it. So now let me talk about the toy model. Toy model is a conformally coupled scalar, just one state with polynomial self-interaction. But now in a power law cosmology. So we're going to go away from the Sitter space or quasi the Sitter space or inflation power law cosmology. So the Lagrangian of the theory, I'm going to have a kinetic term. I'm going to have, so because it's conformally coupled, I tune the mass. It's a little bit funny, but okay. We do what we can, right? And then I write some coupling constants. P factorial, some polynomial, and a power law means that the scale factor of the universe, so the metric of the space-time is given by this. A of eta, I'm gonna write like this. Actually, we wrote it like this because we just wanted to deviate from inflation a little bit. So from the Sitter. So the Sitter space is epsilon equals 0 in this parametrization. It seems that it's a very crude approximation, but sort of all cool cosmologies are specific values of epsilon. So epsilon equals 0 is the Sitter. Epsilon equals -1. Well, we know what it is. It's flat space. -2. It's some radiation-dominated universe. -3 is some matter-dominated universe. So okay, I can't do lambda CDM, but I can do all the bits and pieces of lambda CDM, and the cost of making the mass of this scalar field time dependent. Okay. So this is the model. It has very well. Okay, we thought it had very little to do with reality, but. Maybe I will not say. You can take the correlators from this model and really think of them as a skeleton that if you add enough bells and whistles, you start to get closer and closer to the realistic setup. So it's not such a bad model. It has a beautiful flat space wave function. So if you focus on the flat space correlators, not the scattering amplitudes, the correlators, just the 0 to n type of correlators at tree level. There's a beautiful structure behind it, and it's related to these objects called cosmological polytopes and cosmohedra, and so on. So they're all rational. So that's the reason why they're so tractable. So for this case, the correlators at tree level, they're always rational functions of momenta. For generic epsilon, they are complicated generalizations of hypergeometric functions and so on. So to change epsilon, the analytic structure changes dramatically. Okay, so this is the model. So the question is, how do you find differential equations? And let me try to give you a taste of how we do it. We'll do this simple example. So the first step is to sort of absorb the mass in the Fielder definition, phi to A of eta to certain power times phi. So that now phi becomes just a massless, the classical mode function for a given wave number. It becomes the usual flat space. So you can think of this theory in two ways. You can think of it as a cosmological theory in a specific background, or you can think of a theory of a massless particle in flat space. That's why we like this mass term so much, but with time-dependent couplings. The time-dependent couplings look bizarre, but it's because you did the Fielder definition. So the lambda p, they get mapped to this lambda p minus eta to minus 1 plus alpha p, where alpha p is given by this, 4 minus p. This is not a very interesting formula, but I just want to highlight two cases. P equals 3, alpha 3 is epsilon, and p equals 4, alpha 4 is minus 1. So you see, when it's a quartic interaction, then it's a conformal theory. So you really don't care about the scale factor. Okay, so it's really time independent. When p equals 3, then the coupling constant, the time dependence is 1 plus epsilon. Okay, so the cosmology appears quite explicitly in the time dependence of the cubic term. For generic P, the cosmology appears in a more sophisticated way. Okay. So now what does the 4 point, so the 3-point function is too simple in this model. this 3-point function is just a power law that is controlled by the alphas. But the 4-point function is already interesting, so let me show you what the 4-point function looks like. I'm gonna write just the S channel. You can just sum over permutations. First of all, if I have more particles and only one propagator in the bulk, the formula is not going to change much. It's just the lambdas that you stick in here that will change. If I do 4 points, then it's lambda 3 here, and here. So what's the final result? The 4-point function depends on K1, the spatial momentum. These are the 12 pieces of data that I have, the positions or the Fourier modes of these 4 particles. A little bit of notation. X1 will be given by K1 plus K2. K is just absolute value of a momentum. X2 is K3 plus K4. And this exchange momentum I'm going to call Y. Okay, so Y is the absolute value of K1 plus K2. Okay, so this is just notation to write a neat looking formula. And even though it's 3-level, it's something that you learn on lecture 2 of QFT in flat space. It's going to give you an interesting time integral. So the correlator, the 4-point function, or the wave function of the universe for this process, meaning what is the amplitude of probability that you have a history with these 4 background waves with given wave numbers, is going to depend only on x1, x2, and y in this case. Why does it depend only on x1 and x2? Because the mode functions are just e to the I k eta, and the interactions are polynomial. So when I multiply, when I fuse these 2 wave functions, it's clearly only a function of k1 plus k2, right? Well, here is just a function of k3 plus k4. That's why I'm just simplifying notation. It's given by this formula. This is the formula. If you have a fancy Mathematica package, you can do it. If you have just Mathematica, you can't do it. But this can be written in terms of 2f1 functions. So it's if epsilon equals 0, it's a dialog. If epsilon equals -1, it's of course divergent. But if you send epsilon to -1, you can strip out the leading divergence, and the coefficient up front is a rational function. And it's in fact the integrand when you set these integration parameters to 0. Okay. And so another way of writing this is integral 0 infinity dx1 dx2 x1 x2 to the epsilon times the correlator in flat space. When you take each of the axes and shift them by these little Feynman parameters. Y. Okay. So that's one way of generating this integrand. So you take the flat space wave function, nice rational function, has lots of neat properties about it. Then you take these external energies and you shift them by these Schwinger parameters, and you integrate against this measure, and you get the cosmological wave function. So this is the FRW wave function. So this is a complicated function, and then the question is, what are the differential equations? So let me make a couple of comments about this about this integral. So first of all, I hope it's clear that it looks like a loop integral, right? There's some propagator, some rational thing. This looks like a dimensional regularization measure. So we immediately, once we massage the integral in this form, we started learning about the QCD tools, like things like twisted cohomology and so on. Twisted cohomology, I know it sounds very fancy, but it's a mathematical way of systematizing integration by parts, identities, and partial fractioning of the integrand. Okay, so for example, here, if you look at the integral in the 2D plane, little x1, little x2, you integrate over the upper quadrant here, but the properties of the integral are determined by the locus where the integrand diverges or has some cuts. In this case, there are 5 such lines. So when this equals to 0, it's a specific value of x1. This is line L1. And likewise, this guy, I'm important, L2, L2, L1. Then there will be an L3, this guy. Oops, I messed up, okay. Let's go close enough. L3. And then there are the 2 lines at the origin, so it's important to work a generic epsilon to think of that. That's why it's called twisted cohomology. So it just, I work a generic epsilon to be able to throw away boundary terms without worrying about them and hope for the best. Okay, when I go to the value of epsilon that I care about, there's no more color, but there's these lines here, x1 and x2. So now come all sorts of amazing mathematical theorems about these types of integrals. So theorem number 1 tells me that if I have the space of all integrals, they are only singular, the integrand is only singular along on these 5 lines. So you could imagine, for example, squaring this guy, cubing this guy, putting x1 and x2 in the denominator. There are infinitely many such integrals. The first statement is because of integration by parts plus partial fraction identities, all integrals with this singularity structure form a finite dimensional vector space. Okay. What does it mean? And this is pretty awesome. It means that if I know just a handful of these, I know all of them because they form a vector space. And then the existence of differential equations is immediate, because if I take, let's say we take a span of the vector space, so I take the original integral and more. I haven't told you the dimension of the vector space, so that I have a basis. Now, if I take a differential, I'm just changing the exponents, so I'm still in the same vector space. Therefore, the differential is just a change of basis. So if I take, and that's the differential equation. So you see, so in this model, it's immediately obvious. You quickly solve the question that we set ourselves to solve, which is, are there differential equations? The answer is yes. This is not a very exciting answer because the differential equations can be terribly complicated, not very useful to solve in practice, but it'll turn out to not be the case here. They're very nice differential equations. But at this level, then if you take a vector, or for example, you put the original for W, and then you take other functions, F1, Fn, and they span the vector space. Then if I take the differential of I, which is literally just taking the derivative with respect to kinematics of I, xi plus dgy. Then These are the differential equations. There's going to be a matrix that depends on kinematics, which is just telling me that the differential is picking other vectors in this vector space. So I should just be able to rotate the original members of the vector space and relate these to each other. If you want the differential equations for the original wave function, all that you need to do is take these elements here to be the derivatives of the original wave function. They're going to build other basis elements. So that's it. Okay. So that's nice. Second fantastic statement that was proved by Omoto, Kita, Japanese people that wanted to understand generalizations of the hypergeometric function or the logarithm, is that the size of the basis is equal to the number of bounded chambers. Unfortunately, I don't understand the proof. The intuition is that you put some sort of functional that vanishes along the boundaries, and then you can associate one basis element to something that is peaked around each one of the bounded chambers. And I have some word salad. I don't understand the proof, but I checked in of examples and it's true. Good enough for a physicist. And so here we just find the basis by inspection, right? 1, 2, 3, 4 bounded chambers. So this is a 4-dimensional vector space. So if I know 4 of these guys, psi, FRW, and 3 others, F1, F2, F3, as long as they're linearly independent, I can just stick them in here, run the crank, integrate by parts, partial fractioning, and I'll find a matrix A. Okay? So that's more or less what we did. And the differential equations get very complicated very fast the moment you start adding more legs. So if you, for example, are there any questions, by the way? Clear?
So in this setting, if I hand you some integral of this form, you immediately know how to reduce some linear combination of the 4.
Yeah. Yeah.
And
No, it's not immediately obvious, but the theorem guarantees that I can integrate by parts
so
and
let's say
partial
in
fraction.
practice, I want a large data set of reducing integrals of this type, some linear combination of the 4. Is that
Yeah,
you
you
produce a large data set?
Yeah, yes. I think it's very similar to what people call the Laporte algorithm. You just generate hundreds of shift relations and integration by parts identities, and it's possible. So for example, you associate charges to the sum of the powers of each one of these denominators, and you see that there are relations that lower the power, and you get into a certain level, and then you use other types of equations. So yes, it is possible to do that. We're gonna, the magic here is that we're gonna need much lower brow technology to handle this problem eventually, but.
How do you get out of this wave function, this like these 3-point correlators that you were discussing at the beginning? Like for the non-Gaussianity, for example.
Sorry, what's the question?
So now you have some new thing, this psi FRW.
Yeah,
Before you've discussed mostly 2-point and 3-point functions.
Yeah. this will be a 4-point wave function, and then it's gonna contribute to the 4-point correlator. Okay. So this is a model where the 3-point function is very simple, and the difficulty appears at 4 points and beyond. Okay. And here the motivation was to understand, are the differential equations always there, even if I keep cranking up the number of legs? Right. So yeah, just for entertainment. Actually, the original motivation was to understand this diagram here. Because what is the differential equation doing in practice? It's engineering the Klein-Gordon propagator from the outside. You need to somehow, by shaking and baking these 2 legs here, generate time derivatives with respect to this time, because then eventually you generate the Klein-Gordon propagator acting on this propagator and it collapses it. So then you make progress. And then if you repeat that twice, you collapse this to a contact term that is simpler to handle. That's what the differential equations are doing at this level. And our question is, what happens, for example, here? What am I supposed to do? I only have this leg. Do I wiggle, shake it around, and then I'm somehow able to generate two propagators? And well, the answer is yes. Which we tried for almost a year, we couldn't, from the simple tricks. And from this machinery, you can show that there is a differential equation. So here you have three integrals to do, because the number of integrals that you have to do are related to the number of vertices. So there are three integrations. The number of planes now that carve 3D space is nine planes. So 6 of them form a cube. Just imagine two parallel planes forming a cube, and the 3 others, they carve 3D space in diagonals. Okay. So I always ask this question, and nobody ever got it right. But let me, with this preemptive remark, how many bounded chambers do you think you get here? With 6 planes, you just get the little cube, but remember, the planes are infinite. Then you slice it along 2 diagonals, and the third one is kind of transverse to the 3 planes. So how many bounded chambers do you think you'll get? I've never seen this. I try to draw it on mathematics. It's very complicated to make it visualizable. Do you know? Can give a wild guess. It's your time to shine. 25. Okay, 25 bounded chambers. And okay, just the last one. If you had one more, this grows very badly. Okay, very badly. This is something like this, 200. Okay, so it grows very. Okay, I don't. It's 200, 200. Who cares? It's 200. Huh? It's like 200 by 200. The matrix A. So this looks terrible, but it turns out that these are very special integrals inside of this cohomology. So actually, this is a huge overcount. And the answer is 16 and 64. Okay. Well, okay, it's still not great because it's a theory of 64 by 64 matrix, which we did by brute force. So question number 1 is why. So the answer is 4 to the number of propagators.
Are you saying that this math argument is overcounting the
Yes,
masters?
That's right.
So
Yeah.
is the reduction symmetry or?
Well, it's because the original integrand that you start with is a very special integral. It's not a generic integral with singularities in all of these planes. So somehow if you choose the right basis and you keep taking derivatives of this function, you don't explore the entire cohomology. It's not necessary. Okay, so that's I'll give you a physics reason why the base is much smaller in a second. There is also intersection theory explanation that I don't fully understand by Dan Prokaka, but this is the right answer. The basis is 4 to the number of propagators. And are the differential equations simple, useful, interesting? And the answer is yes to all of these. They're simple, they're useful, they're interesting. And 4 to the number of propagators, it's because of the following. So what are the differential equations doing? Remember that the intuition was that I'm somehow supposed to kill the propagator and then collapse the diagram to a smaller thing. So if you look at the propagator has naturally 3 terms, okay? It's not the usual Feynman propagator, which has 2 terms. So this one has 3 terms. That depends on some momentum y. is given by a formula. For a massless field, it's very simple. It's given by a formula like this. One-time ordering. We have to do canonical quantization. Okay, so back to UFT 101. Now there's a new. Let me put this observational surface at eta star equals 0. So now there's a new term, which is what people call the bulk-to-bulk propagator, that breaks time translation symmetry, because I need to pick a surface in which to do the observation. Okay, so this is, and the plus is not a typo. It's what enforces that the propagator vanishes as you send either eta 1 or eta 2 to 0. So this, there's a graphical way of thinking about it. So the propagator between eta 1 and eta 2, you can think of it as a term in which you have one specific time ordering, 1 to 2, plus a term with this time ordering, 1 to 2, minus a term that we call disconnected, okay? So that the time 1 and time 2 evolution happen independently. So if you take for every propagator, instead of taking the original wave function, that you need to integrate this product of propagators, and you stick one of those terms at a time, you're going to generate 3 to the n integrals. And that explains 3 to the n for the basis. But why is it 4 to the n? It's because eventually when you hit this with derivatives, you're going to collapse this. So the propagator solves that box G equals delta. And this is the fourth term. So there will be a fourth term, which is you substitute instead of the propagator, you stick in sort of, and this I don't like because it has dimensions, so you can just write something like this, the one delta of eta 1 minus eta 2, and this would correspond to essentially just taking the 2 points and taking their coincidence limit. Okay, so if you stick in these 4 choices, you build the basis, and that's the physical basis in which you can find the system of differential equations. Okay, am I out of time? Is that right?
Yes.
Okay. Very bad. It's no time seminar, very bad time management. So
Will eventually emerge.
time to stop emerge. So what happens when you start? Of course, this is 16 by 16, 64 by 64. So at some point to bookkeep, we started drawing pictures of these equations. And then we discovered that you can just draw the pictures and predict all the differential equations without touching at the time integral. So now I want you to suspend a belief in the laws of nature and just indulge me for 2 rules. One is called activation, and the other is called merge. So what is the idea? I'm going to trade each. So you see, everything only really depends on these propagators. So I'm going to have some graphical way of keeping track of these different timelines. So I take the wave function. Let me just draw the. Let me draw. And then I'll explain. Okay. So these we call tubings of the kinematic space. So this is kinematic space, even though it's a 4-point function, because it's only the S-channel diagram. There's really only one interesting axis. So there's the momenta 1, 2, 3, and 4. But because it's S-channel, you can draw sort of the dual diagram. So this is the S-channel diagram. And you can trade the momentas K1 plus K2 by this little ball here. And this is the exchange momentum, which is this edge here. And then this other ball is K3 plus K4. So that's to say that this is X1, this is X2, this is Y. And I need a little cross here because the differential equations are characterized by singularities, denominators. And there are two types of denominators that can appear, which are X1 plus Y, X1 minus Y, X2 plus Y, X2 minus Y, and X1 plus X2. So the exchange momentum can appear with plus and minus signs. So this little cross is to take that into account. From the point, so this is all boundary kinematics. From the point of view of the timeline, it's just parameterizing each one of these histories or this one. Okay, so this guy is sort of equivalent, to, let me call this guy 4. This is equivalent to 4, and then this is these two are equivalent to these two guys here. 1 and 2, 1 and 2, and this disconnected thing you see, I just circled them separately. This is related to 3. The original wave function is just a linear combination of these top 3 guys. Remember, you're sticking the 2 timelines minus this guy. But I claim that this is the right basis in which the differential equations are very simple. And then these funny tubes, they have double duty in life. They show the functions that are supposed to appear, and they show the possible denominators in the differential equation. Okay, so what are the rules? And I see I'm very over time, so let me explain the rules, and then if you want, you can stay after, and I'll show how they work here. So the first rule, called activations, you take each one of these, they have little tubes, and you paint the tubes one at a time, okay? So you paint either this guy or this guy, and when you paint, what you do is you tell one denominator that appears in the differential equation. So if I paint this guy, there's a denominator associated with this ball, this guy, another denominator. So you see there are 5 choices, this little ball, or this guy, or this guy, or this guy, and they're in one-to-one correspondence with these 5 denominators. So that's the activation. And the other is merge, which is that when a tube is next to another, and there's a little fine print, then they're allowed to merge. So for example, when I hit this function here, I'll allow them to merge. Therefore, this function is going to appear in the differential equation because the tubes can connect to each other. The physics reason is that if I hit things with derivatives, with this time ordering, I'm allowed to collapse propagators. And so that's the merge rule. And if you stay after I finish, I can show you that now any 3-level graph, you can generate any line of the 4 to the n by 4 to the n matrix by just following these 2 stupid rules, okay? You just draw some tubes, you paint them, they merge and they connect, and they encode all the time evolution. So that's it. So it works very nicely for this toy model. You can add bells and whistles to the toy model and get closer to the real world. I am confident that there will be similarly simple rules, maybe with some additional bells and whistles that capture this time evolution without ever talking about explicit time. So with that, I think I'm ready to stop. So, yeah.
Yeah. So with these rules, you can predict the matrix elements of this A.
I can predict all the entries of the matrix A. So it turns out that the matrix A is very simple. I didn't say, but if you follow these rules, you'll find that the matrix A is upper triangular. It's very sparse. Most of the entries are 0. And These functions organize themselves into little blocks. Each block has its own life. So as the graphs become more complicated, it's not that you really need to start from scratch. You can sort of recycle. Well, it's simple to see, right? Because if you collapse, it goes back to single exchange. So here, it's not that you really need to understand 16 new lines. Many of them are recycled from single exchange. So all of these recursive things appear in the theory of the matrix A.
The fact that it's upper triangular in most of these poles is pretty natural, right? This happens for Feynman diagrams all the time. You can only pinch propagators, you can never generate new ones. But there's these two special lines, x1 equals 0 and x2 equals 0, that have these non-integer powers.
Yes.
So for those ones, like everything should couple with everything else.
What,
Same as I do analytic regularization.
No, the way they appear is they control the size of each letter. So what I didn't tell you is when I generate denominators, the coefficient in front of each denominator is controlled by those exponents. So there was the integral, dx1, dx2. Let me make it generic, x1 to the alpha 1, x2 to the alpha 2, times some flat space wave function. So these alpha 1s and alpha 2s, they will multiply the letters. So in the rules, when I say activation merge, what will multiply each of these denominators is alpha 1 or alpha 2 or their sum and so on. So that's their role in life. So, yeah, when we found these rules, it was amazing. We could predict all sorts of things, and they were mysterious. And in the paper to appear, we can prove them. It's actually really, really stupid to prove them, but you need to go back to the time representation of the integrals, then you can prove them. It's essentially integration by parts, and yeah, when you hit the derivative and integrate by parts, you hit the theta function, you collapse into a delta function, you generate these terms. And it's bookkeeping once you know more or less what to do.
Do you expect technology like this to generalize to more realistic?
Yes, I do. I still don't have a working example, but for example, if you take this psi flat, I told you about one deformation, right? For which all this beautiful structure exists, but there are other deformations. In fact, I don't think we understand all possible interesting deformations, but I mentioned a couple. So if you take psi flat, and you take the external energies, you need x plus x, and you keep the exchange energies untouched, integrate. That's the cosmology, the F or W, right? Now, another thing you could imagine doing is this. You don't touch these guys, you rescale y, and you integrate against this kernel here, t squared minus 1 to the delta. This would correspond to exchanging a non-particle, a CFT primary of conformal weight delta. Now you can do a more sophisticated version of this deformation with T1 and T2. You need to introduce two deformation parameters for each propagator to generate delta 1 and delta 2, the growing decaying mode of a massive particle in de Sitter space. Now you start getting closer and closer to reality, so you can get de Sitter correlate. And they fall in the same category of integral hyperplane arrangement and so on. The case where I really think that you need new technologies at one loop, because the loop measure really messes up this beautiful structure. So there's a nice story for the loop integrand for doing the time integrals, but to do the loop integral, I think one needs maybe new ideas. For the bubble, everything works. For the triangle, we'll see. There are probably other deformations. I know of another one that you could imagine putting here an exponential of x with some parameter tau, and this would correspond to shifting the Schrödinger wave function by an amount tau in time. For those, the differential equations are not very useful. They're just the Schrödinger equation, but it's another deformation. And there might be others. They're just these are being discovered as we speak. We don't have a general theory of the deformations of the integrand. So I think that if you proceed systematically in this direction, you'll be able to continue finding the simplicity in the differential equations. But the number of basis functions will probably grow. That's it. Okay, thank you.